It's okay.
Yeah, if you're comfortable, I'm recording my presentation. I hope everyone is okay with that. Okay. Good morning, everyone. My name is Anomaly, and I'm presenting our work, AdeNet Deep Learning Architecture that identifies damaged electrical insulators and power lines. And this work is in conjunction with Leo Shamir, William Su, who is my PhD advisor, and Tom Thesis, who is an MS student. Leo Shamir is a collaborator. Okay. So I'll be talking about the introduction, the related work, proposed approach, the methodology and experimental design, the result and discussion, and we look at the conclusion. In the introduction, we all know how important it is, electricity is. Without electricity, this place will be dark. We can't even operate anything. And so, an important piece in the electrical component are insulators in our power lines. They ensure that the carriage of electricity from the generation station to the domestic homes electricity is being able to carry it out over very long miles. And in order to be able to preserve the problem of high voltage discharge around the areas, you need insulators to be able to sustain this high electric current. And these insulators are not immortal. Over time, they get continually exposed to hazard weathers, and as a result, they get damaged, and their damage can lead to loss of electric supply from the generation to the consumers. So identifying damaged electrical insulators is a critical safety task which requires expert electrical engineers to fly helicopters or drones to inspect our power lines and make sure that the electric insulators are in good shape and electricity is in constant supply. So then automatically detecting anomalies in image data has a broad range of applications, because when these insulators get damaged, they constitute an anomaly. Then being able to develop an automated system that can assist human is of great demand in this area. However, anomaly detection is a very hard task, as we will see. So another problem is that training data for such kind of problem is often imbalanced. We always have one particular class overwhelm the other class. And so it's difficult to be able to train most of the state-of-the-art models on such an imbalanced data set. So I quickly look at the concept of anomaly detection, which is finding unusual patterns in image data. You can say finding deviations from the pattern, the normal pattern. And unusual pattern could be a whole image in our own case, or it could be some part of the image. So in this particular scenario, if we have an insulators, there may be part of the insulators that are actually constituting the anomalies. And as a result, it renders the entire insulators to be abnormal. Then the class imbalance, typically we have a skew data where one class is more than the other. So the related works in this area normally focus on what you call one class learning. In situation whereby you just take the normal classes, the normal data point, and you learn your model on that normal data point, and expect that the model will be good enough, quote and unquote, memorizing the normal patterns, the normal images. So at test time, then you can use that model to be able to, sorry about that, you can use that model to be able to learn to discriminate between the damaged and the undamaged insulators, since it has learned the normal insulators, the undamaged ones. So these are the state of the art in that direction. Uh, Anomaly, generative adversary network, uh, structural similarity autoencoder, CNN feature dictionary, variational encoder, and GMM based tech architecture. But in our own work, we didn't use this method. We didn't use learning a model on just a normal data point. And the reason being that when you have a newly manufactured insulators and you learn your system, your model on that newly manufactured insulators, by the time we deploy the insulators on the power lines, after 1, 2, 3 years, those insulators will have changed in color, they will have changed in look, but that doesn't mean that they are bad. So if you have learned a model on the art of factory production insulators, there will be a lot of false positives, because it will be telling us that an insulator that has been on the power line for 1 or 2 years is now bad, which is not. So as a result, these methods will not be the right direction for us to explore. So thereafter, we propose to approach. First is the shallow learning, and we have a tool developed by a collaborator, professor, called UDAT. And UDAT is a statistical analysis tool. This tool is able to extract a large set of close to 3,000 numerical image content descriptors from raw pixels and transform the raw pixels. So it generates the most significant features from images, and based on that you can now learn the normal machine learning classification models like random forest, like decision tree, like support vector machines, and all of that. So exactly that's what we did. So we got our insulators and we used UDA to extract these significant features and perform some machine learning data mining stuff on that. Another approach we looked at is the deep learning approach. And in deep learning, we have multiple layers of mini algorithm, which is referred to as neurons, which work together to be able to make sense out of our data. So in the deep learning, we look at a number of the state of the art that are published in literatures. Efficient Net B7 is one, VGG19 is another, and ResNet 101. These are models that are being proven to work on large data set like ImageNet, which has like 1,000 categories. But unfortunately, all these models fail to give us results, as we will see shortly. And thereafter, we decided to look at what we can do on our own to develop our own proprietary deep learning model that will be able to do the work very well. And that is where the AdeNet comes in. So here I give us a quick overview illustrating the power line and giving us our data set. We have close to 1,500 training plus validation images of power lines. And we did some data preparation, data preprocessing, by first extracting, locating where the insulators are. I think this can point, okay? It disappears. So locating where the insulators are, those insulators in the power lines. And these insulators come in various shapes and locations and orientation. These ones are vertical, some comes horizontal, some comes dual. So we extracted those insulators from there, and we have the damage to be around 1.5 and the undamaged to be close to 3,000. As we can see that distribution, we already have the number of the undamaged insulators roughly twice that of the damaged one. And this is an inherent problem in machine learning. When you have one class a little bit more than the other class. Most of the machine learning models, we categorize the samples as the majority, and which is what we experience as well. So our AdeNet architecture is a deep learning architecture, a very simple architecture but very effective, uh, suitable for the work of flying drones. With 3 layers of convolutional neural network, we use batch normalization, max pooling, and retrieval linear units as our activation function, and there were no dropout. So the fully convolutional layer has 32 filters and kernel size of 3 by 3, and the trained model is just 1.3 MB, which makes it very, very efficient for embedded mobile systems that you can put on a drone and fly, and you can do on-site analysis of the insulators. So I'm sure most of the applications on Apple Store are even more than 1.3 MB. So this is very efficient, and the number of weight parameters that needs to be trained is just roughly 100,000. So out of the deep state-of-the-art deep learning models, the only model that perform comparatively well with our AdeNet is the MobileNet V2. MobileNet V2 architecture is a mobile architecture developed by Google, and it has close to like 400,000 training parameters, which is like more than 3 times doubles ours, and the size is 5.7 MB, which is like 4 times plus higher than ours. And this proves, and if you can see the ROC curve, the one in pink is the MobileNet V2, and the one in yellow, the orange one, is the AdeNet. You will see that the performance is very, very competitive, and we have a gain in the weight, and we have a gain in the parameters. And if we couple these together, we have cheaper computational cost for AdeNet, because you just need to compute over 100, just 100 parameters, 100,000 parameters to be able to make a decision. So these are the results performed on the test set, and we did this experiment on 5-fold cross-validation, and we averaged the result. So you see we have the shadow learning methods here and the deep learning here. In the shadow learning, we tried the random forest, the naive bias, the multi-layer perceptron, and the support vector machine. The best performing classifier in the shadow learning is the random forest, which has a ROC area of 0.82, and the accuracy is 0.79. But in the deep learning, comparing the MobileNet with AdeNet, you see that AdeNet has 0.83 ROC area, and the accuracy is 0.89. However, on expecting the confusion matrix, which I will show us in the next slide, my time should be running out. We discovered that accuracy is not the best performance metrics for this type of imbalance problem, and the confusion matrix revealed that flaws. So you will see here that the AdeNet is having 0.84 F1 score, but when you see the random forest, it has 0.64, which is much more lower, and the MobileNet has the highest there is 0.72. So we're still having a better performance in the F1 score metrics, which is the harmonic mean of precision and recall. So here is the confusion matrix. You see before the random forest, you see that they actually damaged and the predicted undamaged, there is a lot of false positives there. So it's taking the majority as the undamaged, 279. So it's only getting 11 correct, and it's doing pretty well on the undamaged, and classifying just missed out 2. But in the damaged section, which is actually of interest to us, it has missed over close to 300 and just got 11 correct. So this shows that accuracy is not a good metric for this problem. But when you look at the mobile net V2 and the AdeNet, if we consider the diagonal, you will see that we are having a very high number at the diagonal of these two as compared to that. And so this is a more balanced architecture model for this problem. Okay, so we didn't stop at the quantitative metrics. We look at some qualitative metrics by showing some visualization of where the model pays attention to at the time of decision making. And the heated map shows where the focus of the model is during its inferencing. And we can see from human sense judgment that this does make some sense, and it helps us in the area of explainable AI and building trust in our machine learning models for someone to be able to rely on the judgment of this model. In conclusion, we address the task of detecting damaged electrical insulators in power line images. We develop a new architecture called AdeNet, which is efficient computationally and suitable for flying on drones and embedded systems. And in comparison to other approach, we find that our deep learning approach outperforms the shallow learning methods. We have our code on GitHub, which you can access, and also a link to the paper for you to have a full day. Thank you.
So, you said AdaBoost is the best classifier for the normal classifiers. What do you insert into AdaBoost? The full image or?
Oh, I said random forest.
Random forest.
Yes.
Right. I'm sorry.
Yeah.
I was somewhere else.
Okay. So, what do we insert into the? Like I said, the random forest falls in the category of the shallow learning. First, we use the statistical analysis to do that, to extract significant features from those images.
Yeah, which one?
All the images.
What features do you extract?
Oh, what features do we extract? Yeah, it's based on statistics like histogram, HOG, like Chebyshev statistics. There are some image statistics that you can extract using statistical analysis.
Like spectral clustering,
Like spectra, yeah,
analysis.
spectral analysis and all of that. Intensity. So those are the significant features that to
The intensity of the gray level?
Yes, of the pixels.
Okay. Some other questions?
I have a question.
Okay,
What are the hyperparameters that you use in your net?
in the AdeNet.
Mm-hmm.
Okay. Yeah, I specified some of them in the description. Like we use just 3 layers of CNN. We use 32 filters in each of them. Then we use just 3 by 3 kernel size, and we train for 10 and 20 epochs.
What's the learning rate?
What's the learning rate? The learning rate is 0.01. 0.01. I have it documented in the paper. I'm not too sure right on top of my head, but I guess it's a common learning rate that you try. And we use max pooling.
So why do you think the VGGNet and ResNet failed in classifying?
That's a very good question. That's a very good question, and there's a related work in that area. Complexity does not always mean efficiency. Those networks are complex, and they are good at classifying ImageNet, but unfortunately, they fail at classifying this. Number one, right arbitrary, they are not suitable. That's one. Number two, I can say that the architecture is not optimized for this kind of problem. It's not optimized for this kind of task. It's too complex for this task, so it's unable to perform. So then,
Can you go back to the image you showed where you had this transformer of the,
this one,
no, bit more.
Toward the end, you had
this
Yes, this
okay.
one. How do you find this? I mean, you take the full image, so how do you come to this one here?
Yes, during test time, you already have images that you want to test, run your models on. So by the time you pass your image into the neural network, the neural network is going to use its trained weights to be able to make a decision on your input image. And the last convolutional layer will give you a visual representation of where the focus of that system is. Is that a
Can you go
question?
to the first image?
So it's like you extract the last, the classifier,
Yeah,
and you just take the last line.
yes, the activation map. Yeah.
So you only look for the transformers, or do you take the whole image?
No, not the whole image. First of all, you will do the pre-processing by writing a script that can extract the insulators.
Mm-hmm.
These insulators have bounding boxes. Those are part of the pre-processing.
And they
Manually,
go into the net or into the, and these pre-processed images go into the neural net, or?
yes, the pre-processed images goes into the neural net. These power lines they have bounding boxes. Humans drew a bounding box around it. Then we have the coordinates of where the insulators are. Then we wrote a script to crop out those insulators. Then the output now goes into the neural net.
Mm-hmm. I think this is missing, this description in your paper.
Is there?
Yeah?
Is there?
Yeah.
I have a section on the data pre-processing. That shows.
Okay, thank you very much.
Thank you.
I have one question.
Okay, what question? Oh, sorry.
How you train the ImageNet? Did you take the pre-trained model, or you start from scratch?
We use a pre-trained model on image. The TensorFlow, PyTorch has all these models that are pre-trained on ImageNet that you can
Oh,
use.
so you didn't start from
Then
scratch.
we now fine-tune on our own data set. Yeah, you freeze out the base layers and fine-tune the upper layers. Any other questions?
Okay, thank you very
Okay,
much.
thank you. Yeah.
It's a good time to go for a coffee, and after the coffee
Sure.
break, we will go ahead with your talk. So just come with me. We are going to the